Good morning, students. So today we will discuss one more chapter, and this is also first year chapter, chemical bonding and molecular structure. One of the very important topic for NEET, JEE and your Karnataka seat. So very important chapter. So many questions will arise in this chapter. Actually, this is a depth chapter which is having so many points, and this chapter can be divided into various parts. First one is chemical bonding and another one is molecular structure. So chemical bonding, we have so many types of bonds: ionic bond, covalent bond, coordinate bond, hydrogen bond. In case of ionic bonds, we can see how ionic bond is formed and what are the rules for Fajans rule and what are the favorable conditions for formation of ionic bond, and few points regarding the ionic crystals. That is, those points you are going to study in the solids chapter. So that is unit cell, types of unit cell, that is BCC, FCC, SCC, so CCP, like that. And we are going to discuss the properties of the ionic compounds. And next, in case of chemical bonding, covalent bonding, so we will go through with the how a covalent bond is formed. So to explain this formation of a covalent bond, we have a very important theory called VBT, valence band theory. So after that we have hybridization, and after that we have VSEPR theory, and next we will be having coordinate bond, that is dative bond. So a special type of chemical bond, so which may present in only few compounds, that is coordinate bond. So and we have another chapter called coordination compounds. The coordination compounds mainly contain this coordinate bond. And one more type of bond called hydrogen bonding. So hydrogen bonding is also very important point. So hydrogen bonding, and next we have a molecular structure of the formation of a molecule, how structure will be present and what is the electronic configuration of a molecule. So till now you may have heard about the electronic configuration of an atom. So but we can also write the electronic configuration of a molecule using MOT, that is molecular orbital theory. So by using bonding and anti-bonding orbitals, and we have an energy level diagram. Using that energy level diagram, you can write the electronic configuration of a molecule, not for atom. I am telling you about molecule. So let me see one by one points present in the chemical bonding and molecular structure. So first point here is molecular formula charge. So actually the first point begins with the ionic bond. So I told you I am not going to go through with all the points. I am going through with the only important points, that is which may arise in the competitive examination. The first point here is formula charge of an atom in the Lewis dot structure. If you write the Lewis dot structure, how to write the Lewis dot structure? So first you have to write the valence electron of an atom, of an element. So then we have to bond it. So using that we can find the number of lone pairs, number of bond pairs, and all these. And you can find the formula charge of an atom in Lewis dot structure, and that is formula charge of an element of an atom equal to number of valence electron of that atom. So valence electron means outermost valential electron is called valence electron, minus number of lone pair electrons minus half into number of bond pair electrons. This is the formula to find the formula charge. And next point here is the radius ratio. This point also comes under the ionic bond. So radius ratio can be calculated using formula. So radius of cation by radius of anion. Radius of cation by radius of anion. Very interesting point. This is a radius ratio. Actually, this radius ratio value lies between 0 to 1. 0 to 1. Using this radius ratio, we can find the coordination number. That is number of nearest and neighboring atom present with that atom. That is, so using this radius ratio, we can find the coordination number of the ionic crystal. With the help of coordination number, you can find the geometry or structure of the molecule. So here I given various ratios. So that is the radius ratio value lies between less than 0.155. So the coordination number is 2. If coordination number is 2, geometry is linear. Examples. Similarly, if the radius ratio value lies between 0.155 to to 0.225. So coordination number is 3. 3 trigonal planar is the geometry example. Similarly 0.225 to 0.414, coordination number is 4. Geometry is tetrahedral. Similarly, if radius ratio value lies between 0.414 to 0.732, very important, this is very important. If the radius ratio lies between 0.414 to 0.732, then the coordination number here is 6 and geometry is octahedral. Example is NaCl, and here you may get the FCC, CCP or HCP type of crystal lattices. If the coordination radius ratio value lies between more than 0.732 less than 1, so coordination number is 8, and here you will be getting the cubic structure or BCC structure. Example here is cesium chloride. Very important point, remember students. So CCP, HCP or FCC, so this is nothing but octahedral. Example is NaCl type. NaCl type, here coordination number is 6:6. Coordination number is 6:6. Similarly, in case of 8:8, coordination number structure is cubic or BCC. Example here is cesium chloride. So after that, we will go through with the covalent bond. In covalent bond, so here very important point, carbon. Carbon is one of the very important element. You may see that. So you have heard more points regarding carbon in the hydrocarbon chapter itself. And here carbon containing 4 sigma bonds and 0 pi bonds, then hybridization will be sp3. Percentage of S character, very important, percentage of S character here is 25%. So similarly, if 3 sigma bonds with 1 pi bond is there, means sp2 hybridization, percentage of S character is 33.33. Similarly, 2 sigma 2 pi bonds, hybridization is sp, that is 50% of S character. What is the relation between hybridization, percentage of S character? Means using this percentage of S character, you can judge, you can find, you can determine the percentage and electronegativity of the carbon, and that electronegativity decides the acidic nature of the carbon. Relations will be like this: as the percentage of S character increases, electronegativity of carbon also increases. As a result, acidic nature also increases. If you take alkane, alkene, alkynes, hydrocarbon, alkane containing single bonds, alkene containing double bonds, alkynes containing triple bonds. If you arrange these alkane, alkene, alkynes in the order of acidic nature, so order will be like this. So this is increasing order. So first we have alkanes, this is least acidic, then alkenes, double bonded carbons, then alkynes, triple bonded carbons. Among CC single bond, CC double bond, CC triple bond, which is more acidic? All CC triple bond is more acidic. So next we have, so various types of hybridizations will be there. You have sp, sp2, sp3, sp3d, sp3d2, sp3d3, dsp2. So for these hybridizations, what are the geometry and what are the bond angles and what are the examples? Remember, sp hybridization, carbon dioxide, very important, so many times asked in the competitive examinations. Carbon dioxide undergo which hybridization? sp hybridization, remember. So I given this table. So after that you may go through with that. So apart from that, we have so many bond parameters here. Bond parameters. So first one is bond length. Bond length is nothing but internuclear distance between two combining atoms. We already heard that, or we already know that a covalent bond is going to form by combining two or more non-metals together. So if you find the internuclear distance between the two combining atoms, that internuclear distance is nothing but bond length. Similarly, bond angle. So the angle present between two adjacent bond is called bond angle. So we have two types of bonds in a molecule. One is equatorial bond, another one is axial bond. Equatorial bond means the bond present inside the plane, whereas axial bond means the bonds which are perpendicular to the plane. So if you have any lone pair with the molecule, then you have to go through with this point. Remember, very important point. So odd number of hybrid orbitals are there. Suppose for example, if odd means 1, 3, 5. So if odd number of hybrid orbitals are present, then lone pair electrons are written on the axial. Lone pair electrons are written on the axial. If even number of hybrid orbitals are present, then lone pair electrons are written on the equatorial, that is inside the plane. Remember this point, very important. So next is bond order. Bond order is nothing but number of bonds present between two combining atoms. If A and B combines together, between A and B, if single bond is there, bond order is 1. Double bond is there, bond order is 2. Triple bond is there, bond order is 3. That means two combining atoms. Between these two combining number of bonds, that is what we call as bond order. So in case of MOT, we are also going to find the bond order using a formula NB minus Na divided by 2, where NB is called number of bonding electrons, that is molecular orbitals without having star. So Na means number of anti-bonding orbitals, that is molecular orbitals having star, divided by 2. NB minus Na divided by 2. This is the formula you are going to find the bond order in case of MOT. So next is bond energy. So energy required to break the bond. If more amount of energy is required, it is a strong bond. If less amount of energy is required to break a bond, this is weak bond. So similarly, we have another relations here. Bond order is always directly proportional to bond energy. Bond order is inversely proportional to bond length. More the bond length, less will be the bond order. So bond length is directly inversely proportional to bond energy. More the bond energy, less will be the bond length, or lesser the bond energy, more will be the bond length. So next we will go through with the questions. So one more point is there here, MOT, molecular orbital theory. So using molecular orbital theory, we can write the energy level diagram. Using that energy level diagram, you can write the electronic configuration of the molecule. So to write the electronic configuration of a molecule, we have two different structures will be there here. So one is a molecule containing less than 14 or equal to 14 electron. Less than 14 or equal to 14. If you take nitrogen, two nitrogen atoms are there, N2 formula. So here one nitrogen carrying 7 electron, similarly another nitrogen carrying 7 electron, 7 plus 7, 14. This is equal to 14. That means you have to follow this order. So if you take oxygen, O2 molecule, two oxygen atoms will be there. So both oxygens containing 88 electrons, total number of electrons here is 16. That is more than 14. You have to follow this order. So that means what I am going to tell you here is, so the molecule containing equal to 14 or less than 14, you have to write the electronic configuration of a molecule in this order. So these are nothing but molecular orbitals, increasing order of their molecular orbitals, increasing energy of the molecular orbitals. So in case of atoms, you are going to take atomic orbitals to write the electronic configuration. In case of molecules, you are going to take molecular orbitals to write the electronic configuration. That's all. But here we have two different types of electronic configuration. One is equal to 14 or less than 14 electron. One is more than 14 electrons. Okay. So the next important point here is dipole moment. It is a vector quantity. It has both direction and magnitude. So it is calculated using formula mu. It was represented by symbol called mu equal to Q into R, where Q is charge. Dipole means two poles will be there. Polarity is arise. One is positive end, another one is negative end. Due to the presence of opposite ends, we have a name called dipole here. That is mu equal to Q into R. So where charge can be calculated using formula electrostatic unit or coulombs, and distance of separation between two ends, that is calculated using formula using a parameter called meter, centimeter, like that. So here is given they are going to give a standard unit called dBA. 1 dBA equal to 10 power minus 18. ESU refers electrostatic unit. cm refers centimeter. Remember, this unit is of dBA is in CGS system, gram centimeter system. So similarly, 1 dBA equal to 3.33 into 10 power minus 30 coulomb centimeter. Remember, this conversion is very important. Coulomb centimeter. This is ESU in centimeter. So next, to show zero dipole moment, following conditions has to satisfy. So if you want to consider any molecule as zero dipole, so it has to obey two conditions here. The first condition here is central atom should not contain lone pair electron. So in the central atom of the molecule, so if you take a molecule, an element or an atom, it can form more number of bonds is called central atom, and thus central atom should not contain any lone pair electron. Similarly, central atom should be attached to similar subatoms. Subatom means surrounding atoms, and those subatoms should be similar. So if these two conditions are satisfied, then a molecule can be considered as a zero dipole. So let me go through with the questions. First question here is, if electronic configuration of an element, not molecule, element, is 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, 4s2. So the 4 electrons involved in the chemical bond formation. So we already know that to form a chemical bond, only valence electrons are responsible. So which electrons are responsible to form a chemical bond? Only valence electrons are responsible. So in this electronic configuration, valence electrons present here is 3d2 and 4s2. 3d2 and 4s2. In the 3d orbital we have 2 electrons. In the 4s orbital you have 2 electrons. 2 plus 2, total 4 electrons. So they are also given 4 electrons. Hence the option here will be D. So having 3d2, 4s2. This is the right answer here. So next is, which of the following has highest dipole moment? I already told you in the synopsis itself, dipole moment is a vector quantity calculated using formula mu equal to q into r, where mu is dipole moment and q is charge, r is distance of separation. So here they given few examples. For these examples, the molecule containing more dipole moment is water. So these are the standard values. You can go through with the synopsis. So that means you can find the various molecules with the respect to dipole moment. So you can go through with the reference textbooks. So here the given molecules dipole moment. First, carbon dioxide having 0 dipole moment. So HI is having 0.38, water is having 1.84, sulfur dioxide is having 1.64. So among these values, 1.84 is the highest. Remember, water is the molecule which is having very high dipole moment and very high dielectric constant. Hence, the water is considered as universal polar solvent. So next question is, calculate the formula charge of sulfur in H2S based on the length structure. I told you, formula charge can be calculated using formula. So number of valence electron of that atom, that is sulfur atom in this structure, and minus number of lone pair electrons minus half into number of bond pair electrons. So here if you write the Lewis-Dot structure of H2S, structure will be HSH. Sulfur containing 2 lone pair electron, it is a 6th group element having 6 valence electron. Hence formula charge can be calculated. 6 means number of valence electron, minus 4 means lone pair electrons, minus half into 4 means number of bond pair electrons. 2 pairs are there, 2 pair means 4 electron. So 6 minus 4 minus 2 equal to 0. So the formula charge of sulfur in the H2S is 0. Option is C. Next is decreasing order of bond length. Decreasing order of bond length. I already told you, bond length is inversely proportional to bond order. Bond length is inversely proportional to bond order. You may see here carbon-carbon single bond, carbon-carbon double bond, carbon-carbon triple bond. In case of option C, so carbon-carbon single bond. So this is a bond order is less, bond length is more. In case of carbon-carbon triple bond, bond order is more, bond length is less. So this is the decreasing order of bond length. Decreasing order of bond length and increasing order of bond order. Bond order is increased, bond length is decreased. Option is C. So next is the compound with no means 0 dipole moment. 0 dipole. I told you two conditions. Central atom should not containing lone pair electron and subatoms attached should be similar. So in case of first option, we have 3 hydrogens, 1 chlorine. So it's different subatoms. So in case of option C, 2 hydrogen, 2 chlorine. So no similar subatoms. Here also no similar subatoms. In case of option B, 4 chlorine atoms, 4 similar subatoms are attached to carbon, and carbon does not contain any lone pair electron. So this option B can obey both the conditions. Central atom should not containing lone pair, and subatoms attached to central atom should be similar. So this is the right answer here. So next question is the bond enthalpies. Bond enthalpy is nothing but bond energy. Energy required to break the bond. So in kilojoule per mole, we given four different molecules: H bond H, Cl bond Cl, H bond Cl, H bond Br. So where and they given values also. For H bond H, value is 435.8. For Cl bond Cl, value is 239.0, and H bond Cl 431.0, and H bond Br 365. So these values. So bond energy. So which one is the more stable compound? Which one is the more stable compound? In this problem or in this question, they given four different bonds and they given bond energies also, and he is going to ask which one is more stable. Which one is more stable? Stability depends upon the bond energy. So more the bond energy, more will be the stability. More the bond energy, more will be the stability. So where we will be providing more bond energy here? In case of first one, that is H bond H. So its option will be B. So in the next question, which of the following have identical bond order? To find the bond order, first we have to write the energy level diagram, and next we have to write the electronic configuration of the molecule. Using that electronic configuration of the molecule, you can find the number of bonding electrons and number of anti-bonding electrons, and using that number of bonding electrons and anti-bonding electrons, you can find the bond order using formula bond order equal to Nb minus Na divided by 2, where Nb is number of bonding electrons, Na is number of anti-bonding electrons divided by 2. So first one is Cl minus. So in case of Cl minus, bond order can be here bond electrons are 10, anti-bonding electrons are 4, divided by 2, value is 3. In case of second option, O2 minus, so number of bonding electrons are 10, anti-bonding electrons are 7, divided by 2, answer is 1.5. So in case of third option, NO plus, so 10 minus 4 by 2, 10 is the bonding electron, 4 is the anti-bonding electron, answer will be 3. So in case of fourth option, 8 minus 4 by 2, 8 is the bonding electron, 4 is the anti-bonding electron, answer is 2. You can find here option 3, 1 and 3. Option 1 and 3 is having identical bond order. Once again I will repeat here. To find the bond order, you have to write the electronic configuration of a molecule using energy level diagram. I told you molecule containing equal to 14 or less than 14, we have another order. Molecule containing more than 14, we have another order. If you go through with the electronic configuration of the molecule, then only you can find the number of bonding electrons and number of anti-bonding electrons. So once if you know the bonding and anti-bonding electrons, you can find the bond order. So among all these options, option 1 and 3 is having identical bond order, that is 3 and 3, hence option is a C. So both 1 and 3 is having Cl minus and NO2 plus, both are having identical bond orders. So next is pick out the isoelectronic structures. Isoelectronic means having similar or same electrons, In case of CH3 plus, carbon containing 6 electron, hydrogen containing 3 electrons, 6 plus 3. Plus 1 means 1 electron is lost. So 6 plus 3, 9 minus 1, 8 electrons. Option A containing 8 electrons. Option B, so 3 hydrogens, 3 electron, 1 oxygen, 8 electron. So 3 plus 8, 11, plus 1 irodrinda minus 1 ಮಾಡಿ 10 electrons. Ammonia, so nitrogen carrying 7, 3 hydrogen 3, 7 plus 3, 10. CH3 minus, carbon containing 6, hydrogen containing 3 hydrogens, 3 electrons, 6 plus 3, 9, minus 1 means plus 1, 10 electrons. So option B is also having 10 electron, option C is also having 10 electron, option D is also having 10 electrons. Then B, C, D, all these three are isoelectronic in nature, hence option is D. B, C and D. So next is the bond, actually the bond angle between two covalent bond is maximum. Bond angle is maximum, that is more bond angle will be there. So CH4 it may undergo sp3 hybridization. H2O it also undergo sp3 hybridization. I told you in the previous, while telling the synopsis itself, I told you one important point. Remember, carbon dioxide undergo sp hybridization. Carbon dioxide undergo sp hybridization, where the bond angle here is 180 degree. 180 degree. So boron trifluoride undergo sp2 hybridization with 120 degree bond angle. So water with sp3 hybridization, but lone pair repulsions are there. Hence it's according to VSEPR theory, its bond angle is 104 degree. So methane molecule undergo sp3 hybridization, its bond angle is 109 degree 28 units. Among these, so this is the molecule carbon dioxide undergoing sp hybridization with bond angle 180. This is 109 degree, 104 degree, 180 degree, 120 degree. Among these, where you can find the maximum bond angle here? In case of carbon dioxide, because it may undergo sp hybridization with bond angle 180 degree with geometry linear. So next question here is, so the ionic radii of Rb plus rubidium, so plus I minus iodide, and R, so Rb plus is having radius 1.46 and I minus is having ionic radius 2.16 angstrom, 10 power minus 10 meter respectively, the most possible type of the structure. So I told you in the synopsis itself radius ratio. So radius ratio can be calculated using formula. So radius of cation by radius of anion. Here we have two ions, one is cation and another one is anion. So the radius of cation here is 1.46 angstrom and radius of anion here is 2.16 angstrom. If you go through with the ratio, so it is 1.46 divided by 2.16. So you will be getting a answer of 0.675. So this 0.675 lies between 0.414 to 0.732. So if the radius ratio value lies between 0.414 to 0.732, then the coordination number of the compound is 6, having a geometry octahedral, and the type is NaCl. What type of NaCl type? I told you BCC or cubic, that is coordination number is 8. For FCC, CCP and HCP coordination number is 6, and the example is NaCl. So remember, radius ratio is very important for your JEE examination. Okay, so thank you dear students. I will meet you in the next chapter.